Yes.
And so our second story is coming out of the BBC with the headline, "Scientists find, quote, strongest evidence yet of life on distant planet." This is from April 17th.
That's right.
So almost an identical headline.
Yeah.
Different location, potential biosignatures, strongest evidence yet of life, interchangeable. In this case, for the April story, not on Mars.
No.
But on a very, very distant planet.
Yeah.
And this research was coming from a Cambridge team studying the atmosphere of a planet called K218b.
Yeah.
So as a layman, I don't understand what the difference between these two things are when the article just says strongest evidence. Which one is stronger? Is this one stronger? Is that one stronger?
Yeah.
Is it the strongest?
In my opinion, I would say the NASA one is stronger.
Okay.
Okay, because you can literally see the stuff.
Yes.
Okay. And at least what we see, we know we see.
Right.
Okay. With this one, it turns out that the paper that came out on April 17th that was purporting to have seen the things that it sees might not have been seeing those things.
So you're saying don't trust the headlines?
Yes, I'm saying definitely don't trust the headlines. And in this case, also maybe take the scientific paper with a grain of salt. There was a lot of pushback after the scientific paper came out.
Okay.
From the community saying don't say that.
So what's interesting about this April story is, unlike the rover Perseverance being the source of the sort of discovery, quote unquote, it was the James Webb Space Telescope.
That's right.
Another NASA
Yeah,
product.
so there's no tactile evidence.
Right.
This thing's just looking at
It's
stuff.
just looking at stuff really, really far away.
Yeah, yeah. This one's honestly 120 light years away. So in our neighborhood.
Yeah, okay.
Yeah, James Webb is capable of looking, towards
Way,
the beginning of the Big Bang.
The beninging.
Yeah. So this thing is looking at 120 light years away.
Okay.
It's a star called K218. It was discovered by the Kepler Space Observatory. And this is K218b, so it's the second planet to have been discovered there.
The star is K218,
Yeah.
the planet's K218b.
B, yeah. And so the planet is a little peculiar for stuff that we talk about in terms of being potentially habitable, because it's not an Earth-like planet. It's bigger than Earth. It's got the radius of 2 Earths. It's got the mass of 8.
Oh.
So it's one of these like mini-Neptunes, what we call Hycean worlds. We think that there is a giant ocean on this planet.
Okay. Like in that Interstellar scene where they went on the ocean planet and they had the giant tidal waves.
Yeah. Except this would be a lot deeper ocean.
You wouldn't be able to stand.
Yeah, you wouldn't be able to stand and stuff like that. It kind of reminds me of the planet from Dune that was the homeworld of the Atreides
Yes.
family.
Yes.
You know?
Yes.
Like the beautiful blue planet.
Yes.
It's kind of like that. It's a water world.
Okay.
And it's what we call Hycean worlds in the astrobiology community.
Okay.
Right? And so what they think they found is traces of a gas called dimethyl sulfide. This is the gas that you get with like, cooked cabbage.
Yes.
The smell.
Yes.
That's dimethyl sulfide.
It's
Also
a very
like
particular smell.
Yeah. Also like if you're brewing beer.
Yes.
And then it goes wrong.
Yes.
There's a smell.
Yes.
That's dimethyl sulfide.
Okay.
Okay. And that's mostly just made by like phytoplankton on Earth.
Okay.
Okay. So when we found that on this distant planet,
Phytoplankton must be there.
yeah, it's like, oh, dope. And honestly, if we found DMS there and there was no doubt of DMS, then it's a pretty strong it's pretty strong evidence. It's not everything, because again, it can happen abiotically, and that's part of the story that we're going to get to. Okay. So first let's try to figure out how we would even like try to find gases on another planet.
Right.
Okay. On Mars you can like literally just like see it. Right. And then with the Mars Perseverance rover, today's news, it can just go and like, oh, it's like it's shooting X-rays and then it sees it.
It's right there.
It's right there. I'm shooting an X-ray. I get the signature.
Not 120 light years away.
Right. This thing is extremely far. So how do we actually determine what is in its atmosphere.
Right. That's my first question. Is how can we even know that from like a from a sensor system?
Yeah, from a sensor, and that's one of the big reasons why everyone was so excited about the James Webb Space Telescope, is because it would have this capability.
Okay.
So here's the idea. The way we find a lot of these planets is through this thing called the transit technique. Okay. What you do is you stare at a star for a very long time. In this case, Kepler did it for a month. You stare at a single patch of the sky and you look at all the stars. And what the star is going to do is it's going to dim every once in a while for a few hours. It's going to dim. And then maybe 2 weeks later, it's going to dim again. Okay. And then you're going to wait 2 weeks later, it's going to dim again. And there's going to be a rhythmic dimming. Okay. And what's happening is you're getting an eclipse of the planet in front of the star.
Because it's basically like if I'm JWST looking this way.
Yeah.
The star is in the center of my field of view.
Yeah.
And the planet is orbiting around. It's eventually going to pass in between me, JWST, looking at the star.
Yeah.
K218. And it's going to be the whoop. And so the dips you're talking about.
That's going to be a transit.
So
that's why we call it a transit method of finding it.
Okay.
And the way that this thing dips is called a transit curve. Right? You're going to see the brightness because these stars are so far away and they're so small for how far away they are that they're basically points of light. Okay. You can't really resolve a circle.
Right.
Okay.
Right.
You just resolve a tiny point of light and all you can tell is its brightness.
Okay.
Okay. And so the brightness goes down and then it goes back up.
Yeah.
And then it's this rhythmic pattern that tells you that there's something orbiting that star.
Right.
That's happening every, 2 weeks to a month or whatever, and has some cadence, and then you can be very sure that that's a planet that I'm looking at. Yep. Okay. Now, the nice thing about the transit method is, okay, so you're getting a transit curve for the light, right? The light is dimming, but if you have a spectrograph, which is what the James Webb Space Telescope has, it's got a really nice spectrograph. Okay, especially in the infrared region, which is where a lot of gases do quantum stuff. Okay.
Yes.
So if you've got this spectrograph, what you can do is you can get a transit curve for every color.
Okay.
And the trick is that if there is an atmosphere with stuff in it, then the transit curve for different colors is going to be different.
It's going to have a different,
right? Because if suppose there's a bunch of oxygen on this planet, there's going to be a certain wavelength of light that oxygen really likes, and it's going to absorb a lot of. So what you're going to see is a transit curve for every you're going to see a dip in every single wavelength.
Yes.
But there's going to be one wavelength that you're going to see an even bigger dip because the atmosphere is going to be taking out more of that star.
Yes.
Light.
Yes.
Right?
Yes.
That is fundamentally how we use transit method to find atmospheres on these planets.
The chemical composition of the atmosphere.
Yeah, the chemical composition becomes a kind of barcode across wavelengths.
Because the idea is the light's passing through the atmosphere of the planet on its way to JWST. The atmosphere, if it has certain stuff, is going to absorb that light. So that's what causes on the transit curve the dip to be lower than everything else.
Exactly.
There's a high abundance of that particular
substance. Like for example, suppose we had a spectrometer in the UV range. I don't think the James Webb Space Telescope does, but for sake of argument, suppose there's an alien world out there, right? And it's got a telescope pointed at us, and they're just lucky enough that the Earth is transiting. They got to wait a whole year
for it to come back
around. But let's just say they're super patient.
Yes.
When the Earth goes in front of that star, they're going to see a giant dip in the UV because there's a bunch of ozone, right? Yep. And the ozone is what keeps us from having skin cancer, right? But that's fundamentally because it's shielding us from all of this UV radiation. That alien planet, when it's watching the Earth go in front, it's going to see the rest of the light go down because the Earth is blocking it. But the ozone is just going to be completely obliterated. Right?
Because it's so present in
because it's so present, right? And so from that, they can then be like, oh, this planet has a lot of ozone. Similarly, that's what we can do with these planets.
So that's how we can understand the atmospheric makeup, which then from that we can draw conclusions from.
So that's what these guys did, right? They got this transit from the JWST.
Yes.
And then what they want to do is they want to try to figure out what kind of atmosphere would give me that barcode, where this wavelength is a little lower, this wavelength is fine, this wavelength is a little lower, so on and so forth. Right. To do that, now we have to use something like a probabilistic model, this thing called like Bayesian analysis. It's called atmospheric retrieval because we're trying to retrieve the possible atmosphere that created this signature.
Let's say like a barcode.
Yeah.
Right?
So what you do is you simulate a bunch of different atmospheres with a bunch of different density profiles, temperature profiles, pressure profiles, heights, so on and so forth, where the gas is on what part of the atmosphere. And then you simulate what that would look like on a planet with that particular star, because we know what the star looks like, right? We have the spectrum of the star when the planet is not in the way.
So we know
and
exactly
so
what it
from
is.
that, we then subtract this candidate atmosphere one by one, right?
Yes.
And you create this Bayesian model of all the possible scenarios.
Yes.
And you try to see what model best fits
The barcode we see in real life.
this barcode that we see in real life, right? And so this team out of Cambridge from Niku Madhusudan, he fit a bunch of different atmospheres, and he found that the atmosphere that had DMS and DMDS, which is dimethyl disulfide. So dimethyl sulfide is just CH3, two of these with a sulfur in the middle, and then the dimethyl disulfide is two sulfurs with CH3, CH3. Okay. And what he found was that the best model that fit it was something that had a bunch of DMS and 1,000% more DMDS than we find on Earth. And both of these compounds are very much of biotic origin on Earth. Okay? So he publishes this thing, and immediately the BBC, they love tooting UK's horn. So they're like, oh, strongest evidence yet.
We did it.
Right? We did it.
Even though it was with our stuff.
Yeah, exactly. Yeah, like I'd like to see you try and make a JWST. Anyways, so here's the deal though. You read the paper.
Okay.
And the significance level that these guys are saying is at 3.3 sigma. Okay, 3 standard deviations. Meaning the null hypothesis is there's no DMS and DMDS. This barcode that we saw is a fluke. Okay. And this thing is saying that with about 99.7% certainty, 3 sigma meaning you've got this Gaussian distribution of all the possible things that it can be, and we're 3 standard deviations away from that null hypothesis. Okay, so we're 99.7% certainty. Might seem like a lot.
I mean, if I got a 99.7 with the grade deflation we had at Princeton, I'd be pretty happy.
Yeah. Now you don't even need grade deflation at that point, right?
Right. Nowadays,
that's an A++++++. Actually, back then that was a B-. But so 99.7% certainty seems like quite a bit. In science, especially in physics and in astrophysics, that is not a lot. The gold standard is 5 sigma.
Okay.
Which is 99.9999%. Okay. 5 sigma is the gold standard for things like the Higgs boson. I mean, if we had if 3 sigma was the bar for announcing a discovery, we would have discovered the Higgs boson
before CERN.
Yeah. Because Fermilab was doing these experiments already.
Right.
And we were seeing the signature of the Higgs boson, but we didn't do it because we didn't have the 5 sigma level to like actually announce it.
Yes.
So this isn't good practice to announce something at 3 sigma.
So there's a bar.
There's a bar.
So that's sort of like that's mutually agreed upon. That's
by everyone in the community.
You don't publish.
Yeah.
Unless you reach this bar. But then
these guys did it at 3 sigma.
It's funny because I'm looking at this quote in the BBC article from the lead researcher, who said, "This is the strongest evidence yet there is possibly life out there. I can realistically say that we can confirm the signal within 1 to 2 years."
Okay, so he's saying that we can confirm the signal, but then why are you publishing it?
That's kind of
here. The other thing is like a year before like in 2024, I believe.
Yeah.
There was a thing that came out in the BBC that like it said tantalizing signs of possible life on a faraway world.
I love
okay,
the language.
And that was at 1 sigma, 66%.
Yeah, no.
At 66%, I can't believe you're even talking to
media.
the BBC.
Right.
And okay, here's the funny part. That BBC article is written by the same guy who wrote this. Mm-hmm. So I'm not saying what you think I'm saying, but I'm saying that maybe these two guys are like friends. Okay, right. and like they had dinner, and he said, "Hey, I got like, dude, at 1 Sigma, in science at 1 Sigma, you talk to your lab mates about how to improve the Sigma, right? Okay, you maybe talk to like close collaborators. Mm-hmm. You don't talk to the media at 1 Sigma. That's insane to me. Okay,
66%.
Yeah, 66%, dude. Like that's like a bad coin.
Yeah. right.
Like that's so close to 50. Okay. Anyways, but
I get
understandably, 17th of April, this paper comes out. Understandably, there's a lot of backlash from the community.
There's a lot of reviewer number ones.
Yeah. A lot of like. So a week later, this guy Jake Taylor from Oxford. Yeah. A week later, of course. Oxford and Cambridge, they've always had beef. Yeah. This guy comes out and he's like, actually with 5 Sigma, I'm telling you, well, actually, like, so he did 6 different other models. With the same data.
This is the model of the potential atmospheres that could match to the barcode. So the idea is Cambridge said, we looked at a bunch of possible barcodes. We found one that's a really close match.
Yeah.
Now, Oxford came back,
and it's like, well, I did like 6 different methods of doing this, and only one of them showed DMS. But 5 of them don't.
Mm-hmm. So what are you talking about?
Right. 5 of these fits don't have any DMS, but they're fitting with this guy pretty nicely.
The accusation is kind of like you cherry picked one.
Yeah.
And you really didn't do
like an exhaustive search.
Right.
And that was a week after this guy published, right? He's a postdoc. He was just like, no.
About a week ago. A week is crazy.
A week, right? And then about 3 weeks later, the Americans start coming in.
We always do. Yeah.
And because we want a little bit more time. So the Wellbanks group at the University of Arizona, they show pretty conclusively that like propine, which is C3H4 abiotic, can also produce the same signature. Okay, so it's like, well, you have you had like certain constraints on your atmospheric retrieval, but now like once we expand the search, there's all these other molecules that sort of fit the bill. University of Chicago does the same thing with all the data, and they're like, I don't see it.
So everybody's like,
bro, what are you doing? And then actually I looked up. The most recent one is the 18th of July, 2025. UCLA, Caltech, and actually Niku Madhusudan, who is the original leader author of the April 17th paper, he's also a co-author in this.
Okay.
And they say that there's probably water on this thing, like a liquid ocean, given the levels of ammonia and nitrogen and methane that we see, like that level suggests that there's liquid ocean. But he also like pulled back on the DMS.
I was gonna say that's a totally different argument.
So he's like, there's this, and then the one little sentence of the abstract is like, but the DMS could have been made abiotically actually.
So maybe this BBC article needs a slight correction.
Yeah, they really should like put out a little, disclaimer
because.
Or a little asterisk at the bottom being
it's funny. The UK always runs to the Americans.
Yeah.
You need the help.
It's so funny. Yeah.
But there's sort of been a pivot.
Yeah.
In the claim.
Yeah.
Which is like, it's probably a liquid planet.
Yeah.
Okay.
But the DMS stuff, let's just.
So the evidence was not the strongest.
No.
So that's a great way to distinguish when you see headlines and it's like, tantalizing, strongest potential evidence of life. What is evidence of life? What type of life? Is it microbial life? Is it intelligent life? Is it a biosignature? Is it a technosignature? There's all these.
Yeah, is it a potential biosignature?
Is it a potential biosignature or is it a direct?
Yeah.
And so with the rover Mars, the reason why Mars is a great laboratory or great research arena is because we can touch and feel and look. It's right there.
It's right there.
It's
yeah,
tangible,
and we can bring it back.
Yeah, if we fund.
Yeah,
the trip back, which we should, because we want to know that there's aliens out there.
Yeah,
but this is a very good contrast because, as many viewers know, and I know like I work in at a nonprofit that's sort of addressing this unidentified anomalous phenomena issue. It's funny, I actually tweeted earlier today, X posted, whatever people want to say. Yesterday was this UFO hearing in Congress.
Yeah, I heard about that.
In the House Oversight Committee.
And there was like that crazy video.
And there's a crazy video.
Yeah, that looked crazy. I was like, I don't know about this.
It's a crazy video of a Hellfire missile being fired at this object flying over the ocean. It makes contact, but it does nothing to the flight path of the thing that is flying. Mind you, like Hellfire missiles are one of our most sophisticated, advanced. Like it's a problem if it's prosaic or not or anomalous. It's a problem regardless. But the juxtaposition or the sort of fast follow of like that hearing happening, and then I woke up and then NASA's like, oh wait, we might have found life on Mars. It's like, what are you hiding? No, I'm kidding.
And like understandably, like this kind of research and this kind of claim requires an extraordinary amount of evidence
100%.
Because this would be one of the biggest discoveries in human history.
Finding out that life exists
elsewhere
it's in the top 3.
It's in the top 3.
You could argue about whether it's LeBron or Michael Jordan as the GOAT.
Yeah, but like
this is going to be one of those.
It's up there. Yeah, it's either Kobe, LeBron, or Jordan.
Yeah, right. Like it's kind of like that situation.
Like we can all agree that this is going to be a huge deal if it comes out, which is why there's so much scrutiny every time somebody says something, right? Which is why I think reviewer 1 on that last paper was so pissed off.
Went ham.
Right?
Went absolutely ham.